Okay, so we are live. It says there are 8 attendees, but I don't know who or if anybody is actually there. I'm gonna wait a few minutes before I go ahead and get started. If you are watching, if you could just like say hi in the chat or something, maybe. Oh, you guys are on like a 10 to 20 second delay from me as well. We have a question. Yay! Okay, so there is a question and answer function within this. It'll likely pause the live when you enter if you're using a mobile device. If you are on a computer, I don't think it'll pause the live. Yeah, so that's something. That's cool. And you can ask it whenever you want, ask questions. As I go through the actual like lecture portion, I'll probably stop every 5 minutes or so just to kind of come back, see what questions there are, see if you have, you know, you need clarification on anything. I'm going to give people probably like 1 more minute-ish to hop on in, and then we'll go ahead and get started. So when I'm actually doing the lecture, unfortunately, I don't have a separate webcam than the one that you are watching me on right now, and it's really hard for me to write on the screen when it's upwards, and then, you know, my hand would be in the way. So when I actually do give the lecture, I'm just going to put my laptop down flat on the table, so you'll see my ceiling, and then I'll flip it back up when I'm answering questions. Just like a fun fact of things. Okay, so let's go ahead. It's weird talking to you guys and having no one answer, but it feels like we're in the classroom because that's kind of what happens most of the time anyways. So let's go ahead and flip on over to our lecture on simple harmonic motion. Okay, so I'm doing this in OneNote, and the way that I have been doing notes for you guys is probably similar to how you should be writing your review sheets. Okay, so today we're specifically going to talk about simple harmonic motion in mass spring systems. So there's really 2 different ways that we can look at masses on springs. We can have them horizontally, okay, or we can have them vertically. So first I'm going to talk about the horizontal ones because they are A, more common, and B, a little bit easier to understand. So our setup is pretty much, usually there's a spring attached to a wall and then attached to some mass here. And more often than not, the surface is going to be frictionless. Okay, so that should really say mu equals 0. And that just ensures that we really have some nice oscillation back and forth, and that oscillation stays nice and simple. Okay, so if our system is at rest, we call this position the equilibrium position. And I can never spell this word right because I always put 2 L's and there's definitely only one. This position, as long as the spring hasn't been stretched or compressed, is also the natural length of the spring. Okay. So everything's at rest, that's our equilibrium, that's when the spring is at natural length. Okay. From there, we might stretch or compress the spring to an amplitude. So if we compress the spring, we'd be pushing it back to a negative amplitude. If we stretch it, we'd be pushing it to a positive amplitude. In order to do that, we need to apply a force to actually move it outwards or push it back, because that spring, remember, is always exerting a force. Okay, so the first thing we are going to talk about is those forces, and I'm going to set up a table with 3 columns so we can talk about the forces at that negative amplitude, at that equilibrium, and then at that positive amplitude. Okay, so no matter where we are, okay, we always are going to have the force of gravity and the normal force acting on us, and those 2 forces are going to be equal because the net force in that y direction is 0. So when I'm talking about forces, I'm not going to be talking about the y direction, I'm going to be talking about the x direction. So because there is no friction, the only force is the force from the spring, okay? And this is on our reference table. The general equation for the force from a spring is K, the spring constant, times X. So remember that K is the spring constant, and it's measured in newtons per meter. It tells us how stiff the spring is, okay? So this equilibrium position essentially means that our change in spring length, or our x, is 0. Okay, and these amplitude values also give us our x values, our change in length values. Okay, so our forces at the negative amplitude, if we're looking at the equation, is just going to be K times A. Okay, our force at the center is going to be 0 because x is 0, and our force at this positive amplitude is just going to be, again, K times A. Okay, so at this center location here, all of the forces are balanced, okay, and that means that our net force is 0 at that center location because there's no friction, no other horizontal forces. Okay, it also means if our net force is 0, that our acceleration is 0 at that center location, which is weird because we're definitely moving as we pass through that location, but our acceleration is 0. Okay, so at these amplitudes, since this A is the largest we get past equilibrium, that means that our forces are at a maximum at the amplitude, since we're at our largest displacement, which also means that our acceleration is a maximum. Okay, now that's weird because our velocity is 0 at those locations, but remember, changing direction, which is what we're doing at negative A and positive A, is going to lead to that maximum acceleration. Okay. Now, one thing to keep in mind is that the forces will change, meaning when I say forces, I mean Fs. Really, the spring force is going to change throughout the oscillation. Okay, so halfway in between A and x0, our force would be 1/2 Ka, and at 3/4 between 0 and x, it would be, or 0 and A, it would be 3/4 Ka. So that force Fs is constantly changing as we oscillate back and forth. Okay, so let's talk direction of that force, and then I'll check back in for questions. So the direction at negative A is going to be to the right, because we always want to point towards that equilibrium position. So if I'm at A, equilibrium is to the right. Whereas if I'm at this positive A, equilibrium is to the left. So this force is either pushing or pulling me to the left. And then at x0 equilibrium, there is no force, so there is no direction. Okay. I'm coming back for some questions just to check in to see if there are any. Let me switch back to the live stream screen. Let's see. Can tests are due. Everything is good. I have all of you here. I'm going to give you guys another like 30 seconds or so. I think if you join the live late, you start back at the beginning. I'm not really sure how that works. But I'm going to give you guys another 30 seconds or so to ask questions. Again, I'm going to be coming back every few minutes to look for questions if you have them. If we are past what your question already is asked, that's totally fine. You can still ask your question. Don't feel like you don't have to. Okay. Oh, and I am wearing the shower cap. Just for you guys. Okay. Back to some notes, because it looks like we don't really have any questions on this stuff yet. Okay. So after forces, the other thing that we can really talk about with this stuff is energy, okay? Because everything circles back to the beginning of the year. And I think I stressed this a lot when we were doing this topic in class, is this topic is really just a repeat of a lot of the stuff that we have already done, okay? So because there's no friction, energy, remember, is conserved. And in this situation, we're going to convert between spring potential energy and kinetic energy. Okay. So at the amplitudes, we are going to be all spring potential energy. So I'm going to write that as E total is that spring potential energy. Okay. Remember, spring potential energy can be calculated by doing 1/2 K x squared. So if we are at our amplitude, which I have assigned the variable A, we would have an energy of 1/2. Oh boy. K A squared. So if we increase the amplitude, let's say we pull it out a little bit further in a different trial, we're going to increase the amount of energy in our system. Okay. So that's true for both amplitudes. The energy is going to be 1/2 K A squared. Remember, energy is a scalar, so the fact that we're positive versus negative doesn't matter. Okay, in the center here, where x is 0, since x is in the potential energy equation, if x is 0, then that must mean spring potential energy is 0, which means that our total energy in the center here is completely made up of kinetic energy. And since we are completely made up of kinetic energy, this is where we have our maximum speed. And I did forget to mention it, that we are at rest at these two amplitude positions because we're changing directions, which means our kinetic energy is 0 at that location. Anywhere in between those locations, so between an amplitude and equilibrium, you're going to have a little bit of both, okay? A little bit of both kinetic energy and potential energy, okay? One thing to keep in mind, though, is that at the half amplitude part, so like directly in the center here, okay, that half amplitude does not mean that you have half the potential energy in the spring, okay? The reason being is because the spring potential energy is proportional to A squared, which means if we are at half the amplitude, then we are actually at 1/4 of the total spring potential energy. And the other amount of energy is 3/4 kinetic energy. And I think we went through this in your notes. We made a really similar chart to this. Okay. So that's it for this type of problem as far as energy. Okay. So I'm coming back into the live to see if people have any questions. And it doesn't look like we do. We just got more people saying hi. Again, if you have questions, ask them. I'm coming back after each section. Okay. So that was just our section on energy. One thing I did forget to add with energy that is kind of cool, because we directly convert between spring potential energy and kinetic energy, right? kx squared converts totally to 1/2 mv squared. Okay. X and V actually have a direct relationship. So if you double the maximum stretch of the spring, like let's say we brought the amplitude out to 2a, that's going to lead to a doubling in the maximum velocity. These types of relationships are going to be really important, probably on this AP exam, and being able to explain those because they can't really ask you to derive equations. Okay. So the next thing I want to talk about with this system, I'm just going to redraw it here. Bloop, bloop, bloop. 0. We have a negative a and a positive a. Okay, the next thing I want to talk about is kinematics, so positions and velocities and stuff like that. So we most commonly look at these as graphs, and I think with a lot of the classes I was actually able to set up a motion sensor and we were able to look at the graphs of position versus time and whatnot. Now if you remember the position versus time graph, let's say we push this or we pull this out to positive a. It's going to start here. So this is positive a, this is x0, and then this is negative a. We're going to start at positive a, and then we're going to be moving left, which is a negative direction. So that's why we have a negative slope. And then at some point we pass through equilibrium, and then we reach negative a. So we move, then we reach negative a. Then we turn around, and we start moving forward again, this time to the right, which is the positive direction, all the way back to positive a. Okay? And then this is kind of the trademark of simple harmonic motion, this repeating back and forth, back and forth. Okay? Now, you may recognize this as a probably poorly drawn cosine curve. Okay? That is because the position of a mass on a spring that oscillates back and forth can be defined by the equation of a cosine 2 pi times the frequency times time, or a cosine 2 pi over the period times time. Okay. Now, the reason we use a cosine graph is because we start at the amplitude up here. Okay. So some things to keep in mind about these graphs is the slope tells us information about velocity and direction of travel. Okay, so my negative slope here means I have negative velocity, which means I'm traveling in the negative direction. Okay, so if we look, my slope gets a maximum right here where I'm crossing through the equilibrium, which is what I'd expect. And if we look, the slope here, tangent to the curve, is 0 at the amplitude, which is what I'd expect. The other thing we can get from this graph is we can actually use this graph to determine the period of oscillation. Okay, we can do that by figuring out how long time-wise it takes to complete one cosine curve, which I'm shading out here in red. So this is one cosine curve. So let's say this point here corresponded to 2 seconds. That would mean the period of oscillation is 2 seconds. Okay. You also sometimes may be presented with velocity versus time graphs for these objects. Okay. They actually follow the same period thing, but instead of cosine curves, we're going to use sine curves. Because remember, the slope of the position versus time graph tells us velocity. So the slope we start with is 0, and then we have negative velocity and become 0 again. So negative velocity and then 0 again, and then positive velocity for the second half. Okay, and these points here represent our maximum velocity, just in different directions. Right? And anytime we hit a 0 here, this is when we would be at an amplitude. Okay, and notice how I drew my dotted line down to make sure I completed one complete sine wave now in 2 seconds. And this velocity versus time, I would continue as such. Okay. Now remember, the big thing about velocity versus time graphs is the slope gives us information about the acceleration and the direction of the acceleration, which tells us about the direction of the spring force for this type of problem. Okay, so at this location here where I have maximum velocity, my slope is 0, which means my acceleration is 0, which makes sense because that would be where I am at equilibrium. So that corresponds to this point here. I just didn't line up as well as I wanted them to. There we go. Okay, and my maximum slopes, which occur here, are occurring at those amplitude locations. And since this slope is positive, that would mean the acceleration is pointing in the positive direction or to the right, so the force is pointing in that direction. Okay. All right, and then the last thing to do with simple harmonic motion for horizontal springs is the generic period equation. So let's say you're not given a graph and you're asked to find the period. The period of oscillation, which just means the time it takes to go from amplitude, equilibrium, amplitude, equilibrium, amplitude. So basically to go here and back. Okay. So the period is 2 pi square root m over k, meaning mass over spring constant. Okay. Some important things to realize is that the period is not directly proportional to the mass. The period is proportional to the square root of the mass. Okay, and I think we did this as a lab. Okay, so if you double the mass, you're not going to have twice the period. Instead, you would have a square root of 2 times the period. Okay. All right, heading back into the live to see if I have any questions. So the velocity is always greater than 0 or equal to 0. I'm not, well, so yeah, I mean, it can be less than 0 too, because we can have negative velocity if we're moving backwards. For instance, if we're moving to the left, then we're going to have negative velocity. Our velocity is going to constantly change, okay? If we're looking back at the energy chart, yes, we're going to oscillate between 0 and maximum and 0, but in between, we can essentially have infinitely many values up to the maximum, okay? Just the direction is going to change. Okay. All right, so that was it for horizontal. I'm going to do a quick rundown of vertical pendulum, or not vertical pendulums, wow. Vertical springs as well, which are slightly more complicated. I think we did a few problems like this in class, but they are also less often tested. Okay. And again, as you have questions, please feel free to ask them. Okay. So now we're going to talk about vertically hung springs. So any spring that's just hung vertically without any mass in it, on it, is already in its natural length, which I'm going to call XL. Okay? That spring isn't going to do much. If we want the spring to actually oscillate, we have to attach a mass to it. And that mass is now at x0, which is considered equilibrium. Okay. We call it equilibrium because at this equilibrium position, the net force is going to be 0, okay? Which means that the spring force, Fs, minus Fg is going to be equal to 0. So the spring force and Fg are momentarily equal to one another, okay? So this is different than the horizontal one because in the horizontal position, the equilibrium and the natural length of the spring were the exact same length of the spring. But here, the natural length of the spring and the equilibrium position are not the same length of the string. So what that means is as soon as mass is added, there is a spring force and spring potential energy in the system. Okay, so neither can be zero unless the spring oscillates back to the natural length. So unless we push this to exactly XL, there's always going to be a spring force and spring potential energy. Okay? So let's talk about a mass on a spring. Okay, let's say that the natural length of the spring is all the way up here, but the positive amplitude is just below it. Okay, and then here's our equilibrium position, and somewhere down here is our lower amplitude. Okay, and these two I did a bad job of drawing. The positive and negative amplitude are the exact same distance. Okay, so let's do the same thing that we did before. Let's look at the forces in the three columns. So the forces at positive A, x0, and negative A. Okay. So at positive A, Fs is not going to equal Ka. Okay. Even though we are in amplitude, remember that x really represents the change in length. Okay. So this is really going to be K. Let's say A is this distance here. And x0 is this distance here. So our change in length is actually going to be x0 minus A. That part's really not important. Just know that it's not going to be Ka. It's really going to be the change in length of the spring, okay, from the equilibrium. Okay, so this distance is actually going to be very small, which means the spring force is at a minimum at this upper location because we are the shortest distance from the natural length of the spring. Okay, but don't forget we also have a force of gravity acting on us. Okay, the other thing to keep in mind is that this spring force is directed upward. Okay, and that is going to be true for all of these positions because we are heading back to this natural length. We want to be back at the... No, that's not true. That's not true. Ignore that part. Okay. So at positive A, Fs is directed towards equilibrium, x0, not the natural length. Okay. So at positive A, Fs is directed down. Okay. Now this Fg, I can go like this and bring it across because Fg is not going to change. The mass times the acceleration due to gravity is not going to change. It's going to be the same. It's always going to be down. Okay. Now, if Fs is directed down, that means if I was to draw a free body diagram for the mass at position positive A, the spring force and Fg are both directed down. So even though the spring force Fs is a minimum, we can still get a maximum acceleration here. Okay. In the equilibrium position, Fs is going to not equal 0. Okay. Fs will have some value based on the change in spring length. Okay. But yeah. Okay. And then at negative A, okay, again, Fs is not going to equal Ka. Okay. And here, Fs is going to be a maximum, but it's going to be upward. Oh, I think I just... Oh boy. Guys, this is super awkward. I just explained that whole thing wrong because I don't even know. No, did I? No, because there's definitely an FS. No, I didn't explain it wrong. I'm confusing myself now. I've been making too many videos today. Ooh. All right. Okay. So here, FS is a maximum. It's upward. And we still have a maximum acceleration, another maximum acceleration at this lower location where we are changing directions. Okay. So I've thoroughly confused everybody with forces. Oftentimes, you're not going to really look at forces with this sort of situation. The only time you're going to look at them is when you're passing through the center point and your net force is 0. Okay, when the system is at rest. Okay, and that's essentially to get the initial change in length of the spring. Okay, so how far that mass causes the spring to stretch. All right, let's look at energy. Energy, I definitely know what I'm talking about, I promise. All right. It's just like a regular day in class where I mess up all the time and you guys make fun of me. All right, so we have positive amplitude, that equilibrium position, negative amplitude. Okay. So again, we are worrying about change in length of its natural position. So at all of these, we are going to have spring potential energy, okay? Because at all locations, we are stretched past the initial length of the spring, whether we are at positive A here, the equilibrium here, or negative A here. Okay? Now, like I said before, okay, this positive A is closest to the natural length of the spring. So we're going to have a minimum spring potential energy here. Okay, and this negative A is the farthest from the natural length of the spring. So here we have a maximum spring potential energy. Okay, spring potential energy is not going to be 0 in the middle. Okay. The other part that will hold true, even though this spring potential energy is super different, is the kinetic energy is still going to be 0 and a maximum and then a 0 again. That part still holds true because we still have to change directions. We're still going to have maximum kinetic energy through the center. Okay. Now, looking at this right now, it looks like energy is not conserved because we have minimum spring potential energy and 0, maximum kinetic energy and not 0. It just looks like it's not conserved. Okay, because how can minimum spring potential energy with 0 kinetic be the same as maximum spring potential energy with 0 kinetic? Okay, the reason why is because what we haven't taken into account, which is gravitational potential energy. So at this positive amplitude, since we're the highest off the ground, gravitational potential energy is 0. So this gravitational potential energy makes up for essentially the missing spring potential energy. Okay. And then over here, PEG is at a minimum. And depending upon where we set our height, it might be 0. So like if we say that this negative amplitude is a height of 0, that means our potential energy is going to be 0 here. Either way, energy is going to be conserved. Okay, it's just going to be split now, conserved, between spring potential energy and gravitational potential energy and kinetic energy. Okay, and this would be for a spring, block, earth system. Remember, we got to include the earth if we want to have gravitational potential energy. Okay, so we're still conserving energy even though our equations are going to be different. Okay, so that's really what's different about a vertically hung and a horizontal, is this energy part gets a lot more complicated. So does the force part, but like I said, most of the force stuff you can kind of ignore for vertical because it does get pretty complicated pretty fast. If anything, they would ask you about energy. For a mass hung vertically on us, this whole kinetic or kinematics part and the period equation still remains the same. So everything there still remains the same. The only thing that really changes is how we observe the energy. Okay. And really, that's all I had for simple harmonic motion with springs. Tomorrow, I'll do another one of these, but with the forces for pendulums. We're going to look at the energy for pendulums. I don't see any new questions or anything like that, but this is kind of everything I wanted to go over. Sorry that I totally messed up the forces part, but you know, par for the course. I'd want to make sure that you feel like you are at home, you know, that it's like a regular classroom where I always make mistakes anyways. I hope you guys have a great day. I will hopefully see some of you tomorrow. So, bye. Bye-bye.